Hey, dude. Yeah, nice seeing you. Does your microphone is muted or it is my?
I guess I had it muted.
Oh, okay, okay. Well, at least there are two of us, so we shouldn't worry about success of the meeting. Uh, let's wait if more people will join. So, are you visiting Dr. Chilina's lab, Svetlana's lab with Levi? Do you visit Levi and Jabet in their office?
So I've talked to them a little bit, but not a whole lot. Apparently, we're replacing a hard drive tomorrow.
Oh, okay.
So tomorrow I'm going to see Jabet, I think was the one that was doing this with me. Beyond that, I've talked to them a little bit, but not a whole lot.
Okay. I was surprised to see that they all are there. They probably prefer office rather than apartments.
I'm fairly positive that they do.
Okay. Hi, Ivan. Nice seeing you.
Can you
So you may wait maybe a couple of minutes more if you get more attendees. Oh. David, would you like to flip slides yourself, or you want me to do it?
Doesn't matter to me.
Yeah, since you are in on campus, it can work better if you flip. But if there will be if it will be slower than needed, I will be your backup.
Okay.
Oh, okay. Uh huh. Let's check. I think let's start. I hope the recordings will go well, and if someone needs it, we can always offer the.
Okay. So today I'm going to talk about a research update on my layered perovskite project. Um, and as I'm sure members of our group know, perovskite is a material with this structure where it has a general formula of ABX3, where A, which is the green atoms here, are a large cation. B are a smaller cation, they're the blue atoms, and X are an anion. In our case, we're looking at halides. And the main focus of my research is looking at these materials for the photovoltaic potential.
Mm-hmm.
And photovoltaics is the method that we use to convert solar energy into electrical energy. And what we need, and one of the major things we're looking at and is necessary for photovoltaics is charge separation. And then if we look in this corner, I have a schematic for a photovoltaic device. It's and I'm focusing specifically on the active layer. I'm not currently looking at the electron transport or the whole transport layer. And the goal would be to maximize the size of this red square in the figure in the bottom right.
What's the meaning of this figure?
This is an IV curve. So if we could, above this curved line, that is the maximum energy that we could theoretically get from a material. The idea with this shaded area is the power that we actually get, as that is the power that we're actually able to obtain. And it's so the idea is that we want to make the red area as big as possible.
David, I do have a silly question that I was always hesitant to ask in a bigger audience. The realistic device, photovoltaic device, generates direct current. So, so it is specific voltage and specific current. So one needs only one point on this IV curve. Why the whole curve is important? Does it imply that in realistic operation one scans different points on this curve? Like, how do you see this?
So the way I understand it is the area of this curve is important to the efficiency, or the area of the red box or red shaded area. So if we could, let me get out the slideshow for a second. So if we, that's not set up with the way I thought I had it set up. So in theory, we could make several smaller boxes that fill in more of the area. And we'd be able to get bigger potentials that way. Or if we could somehow actually follow the curve, although that's mechanistically probably impossible.
Please correct me if I'm wrong. Does it mean that one is exploring all points and for operational regime select such point on a curve that would give the maximal area?
That would be the general goal, yes.
And it is a natural wish of a human, and it is assumed that any reasonable engineer will do it anyway. So it is not verbalized explicitly. So one would select such point that will give maximal area.
Yeah, and this is just a schematic of this figure. I just put it together by hand with lines and boxes in a PowerPoint here. So this is a very nice looking version of it.
Okay.
But yeah, if you look at the fill factor here, you'll actually see that the areas are involved in the calculation of efficiency.
Okay. And what is MP?
MP is the point of maximum potential.
Maximal power?
Yes, power.
Okay.
So if you look here, we have this voltage is where it has its maximum power output. This is the current where it has the maximal power output.
Okay. Very good. Very good. Thank you. And oh, one more. So this is basics of photovoltaics, but why? Uh, why do you believe that perovskites will give better performance?
So the benefits to using perovskites is they have been shown that they have good potential, but they also have been shown that we can tune them, so we could start filling this box with more smaller boxes. That doesn't make sense, with a greater variety of boxes. So we would have less of this light blue shaded area.
Um, I do not know the answer, but you may just make a note and answer it in the future. If you're telling that photovoltaics is your main goal, then one may want to define. So maybe there are objective reasons that the IV curve will be sharper, and maybe there are some specific elementary features of the perovskite material, maybe because of high dielectric constant or something else. But a reader or a listener would ask this question.
Okay. And so one of the benefits to using these materials is that they are tunable to different energies. So we can vary the size and we can adjust I'm pointing at the photoluminescence. We can adjust both the absorption and the emission of the material by changing the size of the material. And this is from an experimental paper where they looked at perovskites that ranged from N=1 to N=7, as well as bulk. And the smaller ones were blue shifted compared to the larger ones.
So tunability helps for applications.
Tunability can help both photovoltaics and diode properties. For light emitting diode, you can tune the color that you're emitting.
Okay.
Where for photovoltaics, you could make a cell that consists of several different sizes, so it would absorb a wider spectrum of sunlight or light in general.
And
you could specifically choose.
I'm listening.
Or you could specifically choose a wavelength that you know is more efficient at absorbing light, which I don't think I included anything about that in this presentation. This presentation this presentation focuses a lot on light emitting effects more than photovoltaic effects.
Mm-hmm. So, if I understand that we were not thinking about it and preparing a long discussion, but um, I'm, I'm I'm not trying to catch in something wrong. I'm just trying to follow the logic. So, if there is a optimal, there is a best wavelength that gives to provides maximal efficiency of the photovoltaics, in which part of the spectrum this optimal wavelength is expected, and which color, like in your diagram. Um, and I'm not looking for exact answer. Just
if I remember, if I remember correctly, it's in the blue range, but I'm not positive offhand.
But what is the criterion to select this wavelength? To which, what should it compare to? Like color versus what? Should it be related to? We do not need to remember. We need to think. Remembering doesn't help. So one thing, one side, one may tune the absorption gap of the perovskite to the energy offsets of electron transfer layer and hole transfer layer. On another hand, one may tune the gap to the maximum of solar radiation, black body radiation.
Yeah.
Maybe there are some additional factors. There was a work, I always forget the name, but there are scientists who provide the upper limit for efficiency of solar cell. It's like two names written in.
Yeah, I can't remember them offhand. I'm trying.
And
I can't remember the name.
It's like 1960 work, and they develop this consideration, like what should be the gap to provide best photovoltaics.
Oh, yeah, if I remember correctly, it's in the blue region of the spectrum, but I'm not positive off the top of my head.
I'm not sure as well. It could be to the more to the red. And I do see that Aaron and Fatima did connect. So nice seeing you connected. Okay, David, please continue.
So the challenges with this is that we need to, for photovoltaics, we need to examine the charge transfer capabilities of our material. So if our charges don't separate, they're just going to they're not going to create the current that we need to generate electricity. I worded that sentence weird. We need to determine, as we were just discussing, about the most efficient way to properly tune our material, whether that's look for a super efficient absorbance point, look for a wide range. I don't honestly know which would actually be the better of the two. We're looking at the effect of the organic molecules on the properties of the perovskites. And then we're looking at the effects that different layers cause, different layers of the material cause. And by this, I'm looking at two different factors. One is the crystal structure, which is a factor between the materials I'm looking at. I'm looking at either Dion-Jacobson or Ruddlesden-Popper phase.
Mm-hmm.
And yeah.
Other questions? I did hear someone
I thought
was.
I heard someone.
It was like sound of breeze taking air to ask a question.
And the other thing to look at in this situation is if we combine different sized layers of material. So we have one layer perovskite merging into a 3-layer or 4-layer or
Mm-hmm.
different sized layer in general.
Okay. Let me answer on my own question from previous slide. So the I can mispronounce, but these two scientists from 1960s are Shockley Quisser, and if one look for this keyword, I think these old papers are in open domain. One doesn't need to have any credentials, and it gives considerations like what one needs to match to reach maximal efficiency. And they have some estimates of what should be the band gap of a semiconductor to reach maximal efficiency. For I want to be picky to the words. So in the first line, you're telling about charge transfer or charge transport?
Charge transport. I'm rereading this and thinking I did not pick the best words when I wrote this slide.
Okay, because charge transfer it's like between donor and acceptor.
Yeah, it should be charge transport.
And transport is just mobility. Okay. And if you are setting those challenges, do you see? Well, is it? I'm not asking you to answer right now, but for yourself, if do you see a possibility to offer hypothetical answer to each of these challenges? So let me communicate the message. Right now, the challenges are formulated quite broad, like effect of organic molecules. It's an area of research rather than specific challenge, specific question. I would try to formulate it in would the length of organic cation speed up or slow down relaxation or change the dielectric constant. So some challenges in a little bit more specific way that to formulate a question that can be answered in a short way. Do you have any comment on this idea?
That makes sense.
Okay, yeah. So we may try to address it in the next iteration of research update. And for everyone, it is very welcome to ask questions as we go, not waiting until arriving to the last slide. So if there are no more questions, David, please go ahead and continue.
So for this, I was using VASP and PBE functional for everything, and most of the observables that I collected are that we're going to be looking at today are the density of states, some absorption spectrum, some radiative relaxation, and molecular dynamic photoluminescence.
Okay. Are you done with the slide, or you're continuing?
I don't know.
No. If you have something more to say, please keep going, and please give a little room for questions at the end of the slide.
So
again, a comment. When we are speaking between us inside the group, a lot of things are self-evident and understandable, but we are planning such presentations to be as a preparation for later, to offer it later to a bigger audience who may be not aware of our interests and general skills. So it would be really great if one could make connection between the slides in the following sense. So it's not for immediate answer, but in order to address the challenges, we are going to pursue the following observables. So in some way one can make a reverse engineering, and based from results that you already know about, you may explain the methods that gave you these results, and then you can make reverse engineering of the challenges that are addressed by these methods and by these results. So it's an efficient way to tell the story. Do you think it makes sense?
Are you asking me that?
Yes, I'm asking you.
Yeah. Yes, that makes sense.
Okay, thank you. Let's check if there are more questions. If no, let's keep going.
I guess I have two questions for this slide.
Oh, okay.
So I guess my first question is, did you use a spin orbit coupling?
So everything that I'm doing today, I use non-collinear spin orbit coupling.
Okay.
Then it is reasonable to brag about it.
Mm-hmm.
At least, I think everything. Yeah, everything I'm presenting is non-collinear today.
Okay, that's my first question. And then my second question is, it's the connection between your non-radiative relaxation to your radiative. So in your radiative relaxation equation, you have those rho JJ and rho II terms. So what are those, and how does it relate to the non-radiative relaxation part?
So those are the charge densities, and they're related to non-radiative.
I guess what variable do they have in common?
the position.
True. I guess you're not wrong, but I guess they're both functions of t. Yeah, so they're both functions of time. And so I guess they are density, but I think I'm more comfortable saying they're like an occupation density.
Okay.
So it's like they're how populations change in time.
Okay.
That
actually makes it quite.
Let me try to transform the question by Aaron from the point of view how I interpret it, and you please correct me if I'm wrong. So I would interpret question of Aaron in the following way. David, what are the quantitative measures of radiative and non-radiative relaxation pathways? Is there a single number for each of the pathways that allow to compare them? Aaron, did I interpret your question in the right way, or you were interested in something different?
I guess that wasn't exactly my question. I think that's a good question too.
Oh, okay. Thank you for the approval. There is no the question is not supposed to be hard or challenging. It's just free discussion.
Are we talking about the relaxation rate?
Yes, exactly. So which of the pathways gets quicker? Gets is it what will happen first? Optical emission or non-radiative relaxation or recombination?
Non-radiative.
Yes, but we can be a little bit hypocritical in a good sense. At this point, when presenting methods, there are no results, and we can just ask rhetorical questions like, these two processes, each of them has its own rate, and the goal of the research steps in next slides are to find which one is quicker. Would it make sense?
Yeah.
Okay, and then it helps reader to follow, and it makes a self-contained logical story. And you basically told it. One can read between the lines from your narration that you are interested in this, but for non-experienced readers, it's better to verbalize explicitly.
Okay.
Aaron, I apologize if I did cut. If you wanted to continue the question, or if there are more questions from your side.
No, I think my question was answered. I was just trying to relate the non-radiative relaxation to the row terms.
Okay. Okay, I see.
So this is my Ruddlesden-Popper model, and I've given the general formula for a Ruddlesden-Popper perovskite. And as you look at it, you know that there's a offset in the two perovskite layers, and this isn't the best picture to be able to see it, but I tried to highlight it with this red line.
Mm-hmm.
And so this is a cesium lead chloride perovskite, but there are iodines that are used in the layer between the two perovskites that cause it to be offset.
What is specific about this offset rather than it is what it is in geometry? Are there any specific features or any expectations how this structural feature affects characterization, affects electronic structure or optical properties? Or abilities for charge transfer, charge transport?
Well, due to the completely inorganic nature of this model, we wouldn't expect any charge transport to be hindered by this model.
But would the red line will be a good trajectory of charge transfer?
It's not. It would not be a good trajectory.
Uh-huh. Is there expectation to have a potential energy barrier for electron at this offset?
I would expect there to be one. I wouldn't expect it to be very large.
Uh-huh.
I have not specifically looked for that.
Mm-hmm. Okay. So it could be reasonable to say that one may expect a barrier, but the quantitative measure of this barrier is not known or can be not so dramatic. Okay.
Yeah.
Did you check the HOMO and HOMO orbital? Are they delocalized or localized on the spacing layer?
So I did not include the orbitals for this one. They are, the LUMO is spread throughout the entire molecule on the leads, and the HOMO is spread throughout all the halogens, whether they're iodines or chlorines.
Mm-hmm. So LUMO is spread and HOMO is chopped?
No, they're both spread throughout.
Are they continuous in this kink region, or there is a little void in the charge density?
There might be a small void. It's not terribly significant if there is.
Mm-hmm.
I have not thought to integrate the charge density along that axis to actually look at that.
Mm-hmm. Okay. So are there more comments or questions to this slide? If no, I think everyone would be curious to see the next one shown and explained. Okay.
So my other model is the Dion-Jacobson, and in this we see a stacking with a 2 plus cation acting as a spacer, where previously we had a 1 plus. And you can see that in the general formula, where before the A prime, there was 2 of them, now there's 1. And in this model, I am looking at 4 different sizes of perovskite layer. We're looking at an N equals 1 perovskite layer, which would be about right there, would be a unit cell, with this one being the one coming toward us. And here we have an N equals 2, an N equals 3, and an N equals 4 layer.
So it is periodic along vertical axis, right?
Yes.
So the top, it's not hydrogen, it's just organic ligands,
So
right?
that hydrogen there is on this ammonia.
David, I want to play picky and ask for the future. Is it possible to explicitly draw lines between lead and chlorine to have to expose this cubic structure more vividly?
So, like, put a cube on top of it, or like have it set up so there's bonds?
Display the bonds.
Yeah, I can do that.
So it can be, maybe you have some elegant way. I would do it in either of 2 ways. One way is to create a copy of the file in XYZ format having only lead and chlorines, and then move the bond tolerance in such way that it will draw lines, and then show 2 models in VMD.
My idea.
And another thing is to load the model into Vesta, structure, which has option to display bonds between specific group of atoms, and it can be even quicker.
Okay.
I guess you can just do it in VMD. It's pretty simple.
Okay.
And the problem with doing it in B&D is we would also probably end up with bonds between the cesium atoms, so wouldn't we?
Yes.
So you can choose different types of bonds. Just use the dynamic bond.
But Yulun, please correct me if I'm wrong. Dynamic bond in VMD has some, the bond tolerance is kind of homogeneous for all types of atoms. One cannot select different, at least I do not know how to select different
And
bond tolerance for.
that was my thought on it as well.
No, you can do it. You can select different types of atoms.
Okay, would you create maybe just 1 slide of instructions and share with all of us?
Yes.
Oh, thank you so much. It would be really helpful. Okay, David, please keep the steering wheel and lead the discussion. So if no one interrupts you, feel free to.
So here we're looking at the HOMO and LUMO for the N equals 1 model. And we see that in the LUMO, the orbital is localized on the lead, where in the LUMO it's localized on the chlorine. In the HOMO it's localized on the chlorine, in the LUMO it's localized on the lead.
Mm-hmm. Is it natural is it natural or surprising?
That's expected.
Okay.
At least I expected it. What I am not so sure about is in the n=2, both of them are, both the HOMO and the LUMO are localized on the lead.
Let's check if Aaron approves this observation, or maybe there are some comments.
There is some contribution of 6s to the HOMO.
So that, it does appear to be S or
Yeah, so those are expected. But then maybe if you just toggle the isosurface value, like if you decrease it, you should eventually start seeing density on the halides.
Okay. And we see the same effect in the n=3 that we saw in the n=2.
David, do you have plans and intentions to illustrate this, to confirm this observation with projected density of states?
I have been intending to do that, but I have not. I actually need to ask either Aaron or Yulin or you on how to exactly do projected density of states. But I do think that's something we need to look at for this, at least these two models.
Okay. Yep. Because it may be coexisting of like both HOMO and LUMO can be composed of both lead and chlorine, just in different proportions.
Yeah.
Okay.
And for the n=4, we see the expected HOMO on chlorine and LUMO on lead. We do see a slight avoidance of the organic layer in this model. So it's localized toward the center of the perovskite layer. Where in the other ones, we actually had some density even on the chlorines that are interacting with the organic layer.
Okay.
So in the organic layer, are those halides, are they coordinated to the lead?
Yes. So it forms the diamond-shaped structure. I don't honestly know if you can actually see my mouse or not.
No, but yeah, I can see the geometry though. And for some of your smaller models, it looks like there was some bonding for charge and density that kind of leaked in to the organic layer.
Yeah.
That seems to disappear.
Yeah.
For the wider the inorganic layer becomes.
Did you try to measure the distance between organic and inorganic for different layers?
So measure the difference between the nitrogen and the which I'm not entirely sure I understand what you're asking, Evelyn. Are we measuring the distance that this chlorine has compared to the chlorine that's in the inorganic layer?
I guess it doesn't matter. I guess my point is maybe the difference in HOMO-LUMO orbital is just because of the geometry difference. Maybe for n equal to 2 and 3, the model is not very well geometry optimized.
Okay. I have looked at comparing them a little bit to themselves, but I haven't looked at comparing them to each other. That, if I understand the concept you're stating. So here we are looking at the DOS for the density state of the 4 different Dion-Jacobson models, with the n equals 1 being on top and moving down to the n equals 4. And we see that as we go down that the Fermi level increases in energy, and so to question, I think it was Dimitri that mentioned this. So if we do the PDOS, your thinking would be that this peak and probably this peak would have some share between lead and chlorine in the n equals 2.
Hypothetically, before starting calculations and before analyzing, one would expect that it will be just quantitative homogeneous change of properties in the continuous way between different numbers. And here it looks like there are some qualitative changes.
Yes. The n equals 2, it's little, due to the range, it's not the easiest thing to see, but it looks like this the entire way through the entire density of states that I made, from like -6 eV up to 5 eV, I think I made it, where the n equals 4 and the n equals 1 just have a fairly broad peak with a couple shoulders. And I'm looking at the n equals 3, and it looks like it has some of these same features as the n equals 2, just not as sharp. And then there was one other thing that confused me when I was looking at that, and that's the band gap for the n equals 2 is actually smaller than the band gap I got for n equals 3.
Mm-hmm. Oh, did you check the pressure?
No.
Do you have an idea how to do it?
Not off the top of my head, but I know I've read instructions on how to do it.
So I would try to just grab pressure out car and see if anything comes out. And in order to fix it, if there are differences, one may try to practice I'll type in the to add ISIF equals 7 into the in-car and do one more round of optimization. So it should contract or expand.
That's the one that contracts the size,
Mhm.
right?
Yes, yes. And it's only hypothesis. I do not have objective proof, but it could be that in one of the configurations, um, the size of the cell is not ideal. It creates strain, and the strain affects bond lengths and changes the gap.
And here I have the density of states for the Ruddlesden-Popper, and I apparently forgot to change the band gap. It's about 1.6 EV, not 3.4.
Okay. What's that? Absorbance.
Oh.
Okay.
What?
No, I'm just looking. I'm looking.
So here we have the absorbance vector for the n equals 1 model, and we see a peak around 3.5 EV. And this is expected to be the one with the highest absorption of models we're looking at. And
So,
off to the side, I've included a table.
Mm-hmm.
Off to the side, I've included a table that has some of the transitions, including their oscillator strength and energy difference.
So HOMO to LUMO plus 1 is brighter than HOMO to LUMO, right?
Yes. HOMO to LUMO, if I remember, I'd have to go back in the file to check, would have been in this range right here. I think it was 5th.
Mm-hmm.
And for the n equals 2 absorbance, we see several distinct peaks from about 2.1 EV, 2.2 EV, continuing on until the end of the graph at 4 EV. And the HOMO in this one is the 400, in case you were wondering.
So the most efficient is HOMO minus, like balance of -1 to LUMO plus 2. Like the strongest of the lowest. The transition that is likely will provide photoluminescence.
Yes, they would be the LUMO -1 to HOMO plus 2.
Okay.
Did that backwards. HOMO -1 to LUMO plus 2, or plus 1.
Mm-hmm.
Apparently My math is not working for me today. And in the n equals 3, we once again see distinct peaks with the lowest peak HOMO is 536 for this one.
Okay, so it's HOMO -1 to
HOMO -1 to LUMO
+2.
+1, +2.
+2. The second
It's
line,
+1, isn't it?
36 +1. Is the okay, LUMO +1. So the okay, and these are all calculations with spin orbit, right?
What was that?
All calculations are non-collinear spin with spin orbit interaction
Yes.
enabled.
Yes.
Let me ask Aaron if it looks reasonable in comparison to Aaron, to your experience with quantum dots, that the maximal oscillator strength is not from HOMO LUMO, but next couple of orbitals, like HOMO -1 to LUMO +1. How realistic, how standard it is from your experience?
I guess HOMO and HOMO -1 have the same energy, and LUMO +1 have the same energy.
So,
So it's
I'm listening.
we have 4 possible lowest energy transitions. So it's not it wouldn't be wrong to have HOMO -1 to LUMO +1 be one of the most intense transitions.
Okay, so it is a degeneracy.
Yes, there's a degeneracy between HOMO and HOMO -1 and LUMO +1.
Mm-hmm. And since your HOMO has 2 states, and your LUMO has 2 states, essentially, there are 4 possible lowest energy transitions.
Does it match the sketch diagram that I'm showing?
Your screen has been frozen the entire time, like your video screen.
Oh, okay.
So I can't see what you're.
Okay. I will probably disable and re-enable. Did it unfreeze?
No.
No. Oh, I'll just maybe scan and email. But basically, it's the same as what you are telling. It's drawing 2 lines for degenerate HOMO, drawing 2 lines for degenerate LUMO, and then connecting them by 4 arrows for transitions.
Yes.
Okay.
And then for the dynamics, you would expect it to show up in the photoluminescence.
And for if one would follow the occupation of HOMOs and HOMO -1, LUMO +1, they will arrive to about 50-50 occupations, or maybe slightly different, but non-zero occupation of 2 degenerate orbitals while time goes into limit of infinity.
Yes.
Okay, yep, it makes sense. David, do you approve? Do you like this?
I agree with what Aaron just said.
Okay.
I agree with that.
Okay. Very good. Very good.
And we see the same general features for the n equals 4. 2688 would be the HOMO here. So we're looking at a HOMO minus 1 to LUMO transition.
So here it is the strongest and the lowest coincide.
Yes.
Okay.
As for the Ruddlesden-Popper model, we see a structure with 2 peaks with what might be a couple shoulders on one. Definitely one second shoulder. And we're looking at about a 2.2 EV peak for the initial peak. Do not offhand remember what the HOMO is in this one. I want to say it's 216.
David, let me check if you have a typo. If you were typing this table by copy pasting from actual illustrators.
No, I was typing it by hand, so it's very possibly a typo.
So the first line has J equals 1318. It's likely 1218.
That's probably 1218. Yeah, I was typing this out by hand. I wasn't copying it.
Okay. Do you have maybe verbal intermediate conclusions summarizing all absorption spectra?
So we see similar effects for all the Dion-Jacobson models, where we have for all the Dion-Jacobson models greater than n equals 1, where they have several peaks and then the lowest peak corresponding to a degenerate, the HOMO to LUMO transition, whether it's specifically HOMO or LUMO or one of its degeneracies. Where the Ruddlesden-Popper model, we see a significant difference in this 2 peak spectra that has we don't even see a absorption peak for the HOMO to LUMO transition, which is about 1.6, 1.7 EV.
Mm-hmm. Do you have in your long-term plans to redo absorption spectra with HSE functional?
It's definitely a possibility. It's not really in my plans right now, but it's definitely not something I would rule out.
So which
that would give us a much more quantitative view of the results. These can be considered qualitative.
Okay. And do you have in your long plan list, do you want to keep going for more and more layers, or you are tired with 4?
My long-term goal would be to start combining layers. So have a n equals 1 and a n equals 2 together, or something along those lines. We could continue, although my n equals 4 model is around 1,000 atoms. I think it's almost 1,100 atoms.
So I'm applauding and very supportive for this plan, and I was trying to do something like this, building this interface model. So one of the by combining several layers in one simulation cell, one may observe substantial mismatch of the lattice periods. And mismatch of lattice periods creates strain and may screw up and make amorphization or change gaps, so far from realistic. There is a hypothesis that there is a magic numbers, like sharing the same common denominator. So only specific combinations of number of layers will fit each other. And from what I did try myself, and one needs to take into account both thickness of the inorganic perovskite layer and organic spacer layer and their multiplication. So from what I did try to do, the best match and least strain is from combination of I think it was one of them was 5, either 5 and 2 times bilayer or 5 and 2 times 1 layer, but 5 definitely was among the best candidates. And targeting the formation of interface, the n equals 5 is one of the favorite candidates to include into your systematic exploration.
Okay. In that case, it's probably worth at least looking at the n equals 5 layer individually as well.
Mm-hmm. Okay.
So here we have the photoluminescence time resolved and time integrated spectrum for the n equals 1 model, and like like Aaron was talking about, we have this odd peak here based on the degeneracy of the HOMO and LUMO, or but we also see a peak, and this is basically right at the initial excitation value. In fact, it should be right at the initial excitation value, because this is just HOMO to LUMO plus 1. So this was the transition with the highest oscillator strength for this molecule, or for this model.
Mm-hmm.
And it should be noted that the intensity is logarithmic scale as well.
So it's 10 to the power 2.
Yes.
Oh, okay. So would it be correct to say that oh, sorry, I will wait until you show the next slide.
So in this slide, and numbers aren't the best because I just took this from the presentation I did a couple weeks ago. This one, we're looking at a slightly larger initial transition for the same model. In this one, we're looking at HOMO -5 to LUMO +10. And we see that we get our major peak is at pretty much the same level as if we just excited the HOMO to LUMO -1 that the previous slide was. And I'm not entirely sure what all this is. I made a waterfall graph of this like Levi suggested, and I don't see anything in this region on that graph.
Mm-hmm.
So there's might be something going on that I need to figure out down here. But the only things I could see on the waterfall graph were up here.
Okay. Two questions. Or two question and a comment. From the data that you have generated, would it be correct to say that optical range, visible range photoluminescence is independent of the excitation energy, that the transition energy and intensity of the photoluminescence signal is the same or independent of where you excited?
Based on what I've seen, it's pretty much the same. Slight variations in intensity, but not very large, big variations.
Okay. And second comment, for this infrared emission below gap, what is your interpretation of these signals?
If it's not an error somewhere, the only thing it can be is intraband transitions.
Mm-hmm.
Correct?
I'm happy with this explanation. I don't know if it is absolutely correct, but it's correct for me. And yes.
I'm not completely positive that that's not some type of error that I just haven't figured out yet.
So please let's check with Aaron, Yulun, and Fatima if this interpretation sounds legitimate. So David is telling that this infrared signal between 0 and 1 EV subgap originates from intraband transitions. Are there any objections to this interpretation? So no one objects, which means everyone approves.
Yeah, and I guess the only thing you could do just to convince yourself is just to change HOMO -5 to the just HOMO position.
Okay.
Just artificially run the same dynamics. And then do the opposite where you just set LUMO to LUMO +10 to LUMO. And then you'd be able to kind of narrow down whether the contributions came from the conduction band or valence band.
Oh, interesting. That's a nice plan.
Okay.
So Aaron, I like your research plan, and I see a connection with mindset of a researcher of polarons. in this, like to have your suggested experiment would correspond to charge being injected either in valence band or conduction band, and then looking for infrared photoluminescence.
Yeah, though, yeah, I thought about this for like half a year, so it's why that experiment just came to mind. But it is interesting that you have a subgap of like 1 point, well, at least gradient B.
Mm-hmm.
So it's like I would expect like half EV signature to show up, but you see them like up 1.1, which is, I don't know, unexpected, but could be an interesting thing to follow up on.
Okay. So in the n=2 model, I looked at HOMO -3 to LUMO +3. And this one also has a odd infrared peak that I have not looked at this one to see if there's something that I just can't see in this range because of the coloring. And in this one, we see 2 peaks for intensity, one at the approximate the initial excitation, and then one that's once again right around the band gap.
Mm. I do have a technical question. So,
Sure.
where your marker, where your laser pointer is showing at about 2.5 electron volts between these 2 peaks, between the strongest and the least, yes, here. So there is a time resolved emission at 2.5 on the blue diagram, but
Yes.
there is no peak in the integrated emission.
Not.
So I do not have doubts that there is a peak in the integrated emission, but we do not visualize it properly. So are there any suggestions or ideas how to make it visible? Either to start
So
range from, oh, please speak if you have ideas.
So I did adjust the range to see if I could find this peak.
Mm-hmm.
I went down to -20, and it still wasn't appearing.
Huh, interesting.
So if there is a peak, if that does have intensity, which I assume there is some intensity there, it's very small.
What if we do log of the log for the integrated emission, like double logarithm?
Okay.
I don't
I'm
know
not trying that.
if it will bring any success, but just checking.
Okay, I can check that too.
Mm-hmm. Yep, thank you.
So I guess my question would be, is that blue figure, is that like the, I think in the code it's called the Presto?
No, this is not the Presto. This is the one that uses, I don't remember the.
So it's
the one that uses just the generic term. I don't remember what it is off the top of my head. I'd have to go through and look at the code to check. But it's the one that just uses emission or excitation or something like that. It's not the Presto, it's not the Fermi.
So it is the one that is multiplied by oscillator. Sorry, Yulin was giving a comment.
Yeah, I guess maybe you can just double check both this figure looks similar to the exciton figure that everyone is talking about.
Okay.
Because then it would make sense, because the energy gap between the middle bar and then the lowest bar is about the same energy. That's where you see this anomalous peak in the IR.
Okay.
I guess it is also curious too that the middle peak doesn't like decay or go away.
One can probably identify that it gets a little less intense, and the lowest peak becomes more and more intense. And then, David, would you please bring your laser marker onto the time independent peak at 0.3 electron volt? Yes. So this peak, the transition energy of this peak seems to correspond to energy offset between between the visible range transitions, visible range excitations at 2.4 and 2.1 electron volts. And as we get transition from 2.4, as we cascade excitation from 2.5 electron volt occupation to the lowest, it may go both non-radiative and radiative. And if this goes through radiative pathway, it may give rise to this infrared peak at 0.3 electron volts that David is pointing with laser point right now. Would it be a good hypothetical interpretation?
That makes sense to me. Because, yeah, that does look about the same size as that, which I think is what Aaron was saying earlier, or maybe Yulin.
Yeah, that explanation makes sense to me.
Which might also explain the peaks here, because it does look like there's some random up here.
Mm-hmm.
I have a question.
Yep.
So in your previous studies, yeah, so is this intensity scale in log scale or?
Yes, it's log.
Okay.
Yeah, all the intensity scales are in log for what I'm showing.
Okay, so you need to write log 10 base intensity, or it's okay to write intensity? I'm not sure.
I should write log intensity.
Okay. I wrote log intensity in my previous paper, so. Okay, that was my question.
Yeah, it should be log intensity. I didn't change that title when I made the graph. So here we're lking at the HOMO -14th to LUMO plus 15 for the N equals 3 model.
Mm-hmm.
And I chose this model because it had the highest oscillator strength.
Mm-hmm.
Or chose that transition because it had the highest oscillator strength. And we see that around I don't know what minus 0.5 is in logarithm. around less than 1 picosecond, we start to see a transition from the peak at the initial transition down to the peak around band gap.
Mm-hmm.
I was not able to get the time integrated graph to work for this model when I worked for this transition when I was doing it, and
Was it
I need to sit and figure out.
It was an objective difficulty or just lack of time?
More lack of time.
Okay.
When I entered in the code in MATLAB, it just popped up a blank graph every time I did it.
Okay. If it keeps doing it, maybe you can share all input files, and I would be interested to run and see what happens. And if the files are small enough through email, if they're big, maybe just place them somewhere on Photon.
Okay. And I had the same issue with the time integrator for the N equals 4 model, where I was looking at HOMO minus 1 to the LUMO, and we see a peak during the entire time range that I'm showing at the initial excitation value.
Mm-hmm. Mm-hmm.
For the Ruddlesden-Popper model, I'm excited from HOMO minus 3 to LUMO plus 1, and we end up with a relatively consistent peak, but we see at about 3 picoseconds and what is that? 10 femtoseconds? Is that right?
Mm-hmm.
I'm not sure I'm doing that math
Mm-hmm.
right in my head today. We see slight change going from about 2.25 EV down to about 2.2 EV.
So it's a cooperative contributions from several transitions.
Yeah, so there appears to be at least 3 peaks from the way I see it. And if you look right here, you can see a shoulder in the time integrated.
Mm-hmm.
Why there is no intra-band transitions?
At the 0 mark for this one?
Yeah.
I have no idea.
Did you check that oscillators intraband oscillator strength is vanishing?
That shouldn't vanish for this, should it?
Not interband like LUMO plus 1 to LUM oscillator strengths inside the valence band and inside conduction band?
I don't offhand remember those values. I looked at them when I first made this graph, or when I was first working on this graph, this model's graphs, but I don't offhand remember.
So right now the initial condition is HOMO -3. But for
Yes.
intraband transition, you still have HOMO -3 to HOMO -2, which has maybe quite a high oscillator strength.
One more back, energy. Oh, do I remember this command? So yeah, it's a very big oscillator strength value.
So it can be some aspect, like technical error rather than objective reason for absence of this infrared.
Yeah, maybe. I'll have to look at that one.
Okay.
So here we are looking at the MDPL for the models, and we see the expected qualitative trend for the Dion-Jacobson models, which is the model on the left, where the N equals 1 is most blue shifted and the N equals 4 is the most red shifted. There is a shoulder on the N equals 3 model, which I am not entirely sure enough about this technique to actually explain that.
Did you pay attention to the molecular dynamics trajectory? Is there any ligand disruption?
Not that I remember, but that's the. I'm assuming something odd happened in molecular dynamics because that's the only thing I could think of. I need to check that again. But we do see the expected general trend for these models. And on the right, I have the Ruddlesden-Popper model, which shows the peak right around the band gap of 1.6 throughout its trajectory.
This is a 1 picosecond trajectory.
So the N equals 1, 2, and 3 are 1.5 picosecond. The N equals Ruddlesden-Popper are 1 picosecond.
Okay. So Yul was asking about molecular dynamics. So maybe if there will be plan to reiterate and go over this material, so make next update of research after some times, right before this figure, it could be reasonable to show movies of molecular dynamics.
Okay.
So, okay.
Sure, I can add that.
Uh-huh. And for can we look on previous for a few minutes more? So for the n equals 2, no, the MDPL emission. Yes, for n equals 1 and n equals 2, the peaks look quite symmetric in respect to the center.
Yes.
For n equals 3, the feature that you call shoulder is more to the blue side, and for the
Yes.
for the n equals 4, the thing that you call shoulder is more to the red side.
Yes.
So the criterion of absolute truth is comparison with experiment. So is there any asymmetry of the shape of the PL profile in the experimental data? Do the peaks look symmetric, or there is more, like which shoulder is more shallow, blue shifted or red shifted? So it's basically a question to your next slide.
So it seems to be a little determinate based on the size of the perovskite. The smaller it is, the more the shoulder is red shifted. The bigger it is, the more it appears to be blue shifted.
Mm-hmm.
But they're all relative models. The n equals 1 and n equals 2 are the only ones that are real easy to see that there's some shoulder going on.
Mm-hmm.
That could just be because the colors overlapping too, but we
yep.
but we do see a similar qualitative trend as what is observed in the experiment.
Yeah, the trend of quantum confinement making the shift of central wavelengths is outstanding. It's really good and qualitative. What about the width of the PL profile? Is it does theory shows bigger broadening than experiment?
So the theoretical does show a larger than the experiment does.
Is there a quantitative measure? Is it like twice broader, or 1.5 broader, or 3 times broader?
So if we look at the n equals 1, it appears to be about twice. Maybe a little more than twice. And you see similar if you compare other ones, you see a similar twice, except for the n equals 3, which has that extremely large shoulder in the theoretical model.
Is there a procedure, is there an equation to extract broadening in a quantitative way? Like if you have this like purple line as a numerical data, can you extract the width?
So So we're talking about this. There should be.
Okay. And
Off the top of my head, I can't think of one, but
it should be standard thing even without our codes in the group. If there is experimental set of data like a Gaussian line and or like approximately experimental, there is a way to extract width.
So yeah, there's a way to extract it. It's just.
So I do have question to everyone. All of us were trying to do such calculations in the past, and is it standard situation that computed width of the photoluminescence peak is wider than experimental one, or it is a unique feature of this system?
I guess for the quantum dot model that I worked on, it was, I guess, substantially wider. But then again, experimentally, they don't look at models as small as the one we were looking at.
Mm-hmm.
So it's not a direct one-to-one comparison. But usually in experiment, they see the smaller the quantum dot, the wider the full width half max.
Okay.
So qualitatively, our MDL procedure kind of followed along with what's seen in experiment.
Okay. Yeah, thank you.
I guess in this, so your model, the halide is chlorine, right?
Yes.
And then for that experimental paper, are those chlorine?
I believe they were bromines. I know they used methyl ammonium instead of cesium.
So it is not apples to apples.
Iodine.
Okay, iodine. Are there experimental data for chlorines?
Are what?
Other experimental data for lead chlorine progression of multilayer perovskites to compare apples to apples?
Everyone I've seen that involved chlorine also had iodine. But
okay, we may keep looking for.
That's something to look for. But yeah, everyone that I've seen that used chlorine had iodine in there somewhere as well.
Mm-hmm.
I have a question. So for your MDPL, I guess I'm just focusing on the peak position. It is very much different from your density of states calculations. So for density of states calculations, the band gap for 2 and 3 is pretty close. But
Yeah.
here,
so
it's like
I was interpreting that as this shoulder was something toward the end. This shoulder was involved in that. But another thing I need to figure out, because if you look at that shoulder, it seems the point where the band gap seems to be pretty much where the n=2 and the n=3 overlap.
So if the cell size is not optimal, it could be that geometry escapes the configuration with the strain, and then gap expands or shrink. No, here it looks like it shrinks along the molecular dynamics trajectory.
Yeah. That was the only thing I could come up with for why that is, but yeah, I need to put some more research into why that's occurring.
I do have a comment that sounds strange to myself, but so on one hand, theory computations gives wider halfway line width than experiment. But on the other hand, we may target the trends rather than absolute values. And if we follow this attitude, and if you want to reproduce asymmetry of the peaks, anharmonic motion could be insufficient. We may consider the discussion that we all had while being near slides 17 and 18 about the degeneracy. So if the lowest transition happens from HOMO and HOMO minus 1 to LUMO and LUMO plus 1, and if the lowest transition is fourfold degenerate, maybe it could be reasonable to include 4 lowest transitions into the MDPL calculation.
Okay.
It's just I'm throwing in an idea. I don't know if it is reasonable. Just trying to connect it to the previous discussion. Because if the lowest transition is 4 degenerate and there are 4 excitations that may have approximately the same transition energy and they may swap the order along dynamics, then how do we know that? And if if there is no guarantee that the lowest of them will give the highest optical transition, maybe all 4 should be included, and it could be potentially a way to predict lack of symmetry in the emission lines. Okay. Are there more questions or maybe more slides?
So, in conclusion, we see that our model follows the qualitative trends that we see from the experiment. The model is tunable, so we can have control over our results for both photovoltaics and LEDs. And the organic layer appears to insulate the perovskite layers for a model. I also listed a question that Aaron answered during the talk.
David, these conclusions that are placed on the slide seems expected. So the calculations confirm intuitive expectations, right?
Yes.
Which is a good conclusion. But other additional observations which were not expected before calculations were done. So it is okay to report something provocative.
So the localization on the lead, I was not orbitals on the lead, I was not expecting. And Aaron seems to be of the opinion that that's at least plausible to be correct. And the intra-band radiative relaxation rates are also an interesting effect that I wasn't expecting.
Okay. Yep. Well, I invite everyone to join me in thanking David for very long, intense, and thorough processing of the material. Aaron is typing comment that PDOS calculations should confirm that HOMO has contributions from lead and chlorine. Yes. And I also wonder if the HOMO -1 will have the similar orbital as HOMO or drastically different. So if they degenerate, one may expect that they will be similar, but it's better to have either PDOS or orbitals or both. Let's open the paper for discussion if there are more questions to David.
I guess one general question I have is, have you done any sort of K-point sampling for any of your models?
I did K-point sampling for the n=1 model, but I never really got back to looking at what came out from it. And the K-point sampling I did was probably not very useful anyway, because I put a lot of K-points.
How many?
I don't honestly remember. I'd have to find the file.
Just by the order of magnitude, did you put like a handful from 1 to 10, or about 100, or about 1,000?
20 to 30.
Okay, so it's like 6 by 6. Your K-points file was something like 661.
Yeah, something like that.
Okay. Do you know how to extract the momentum dispersion in 2 dimensions out of such calculation?
No.
We can figure it out together. It's not too challenging, but we may consult with Fatima and Braden Wade, who were doing it. So like from the calculation with 2-dimensional sampling, one can extract and make this 2-dimensional surface. For these layered perovskites, I'm not anticipating there will be some non-standard shape, but it's a reasonable to check one day. Maybe there will be.
Okay.
if everything is normal, if there are no special things, it will be like minimum in gamma point and slight increase with a parabolic shape as k vector in, growth. And also there is, if one uses automatic mesh with this Spark Monthorst, it changes kx and k1, ky only between 0 and 0.5. So they both x and y components are positive. But one there is a way to explicitly mention all k points and scan values of momentum from negative to positive, which is a little more numerically expensive, but then the dispersion surface looks better and easier to analyze. Okay. Are there more questions to David? Okay, so let's, if no, let's thank David once again. And if anyone was making notes and comments, please share them with David. I was doing some handwritten comments and will scan and share. So next meeting, there like we have on schedule Fatima, so you may give an overview of the completed project briefly, and then tell about your research plans, and it doesn't need to be long, so we can chat about it through email one by one. And in 2 weeks there will be how to say, guest presenter, a student who was taking course in the spring semester, or no, a year ago, Meet Erickson. So he's practicing the methodology developed by Yulun for photodegradation, and hopefully he will show some interesting results. So I plan to share, I'll check if recordings were done and share them. So if David needs some ideas that were spoken but not handwritten, and everyone is welcome to disconnect. Meeting is done, and I'll stay on the connection just in case if any additional discussions I need.